protocol implementations. Okay, so what you usually do is try to show that, okay, suddenly my algorithm is better than X protocols. But however, you might have got that result based on one particular run. So do you actually accept the fact that your algorithm is better than the other algorithms than X? And then also when you try to compare your algorithms, make sure you compare to very similar algorithms to yours. You don't compare. Let's say, for example, you buy a sport car. You don't go and compare with a truck. You might need to compare to with the same sport car. Okay. And also when you compare between the same sport car, you need to make sure that you race again the same car. I mean, you race with the same car, not just one time, but multiple times. Okay, so in other words, you don't just show that, okay, I beat you one time, oh, my car is better than yours. That's what I'm trying to say here. In other words, at one run, you already say your algorithm is better than X. But could that actually happen by chance? Does it always try again? Or does it always happen? So once I get something better, I'll just say, okay, I'll stop here because I don't want to try it again, just in case I don't get the same result again. Okay, and that you should avoid all those. You should actually try to repeat your experiments. Make sure that you get a certain level of confidence that your algorithm is better than X. Or another thing that usually people might do, which you should, I mean, all this you shouldn't do, but people might actually do is actually they might compare their algorithms on one problems, which is different from X. Okay, for example, I might race my car on a highway versus the other car is driving on a village way, a countryside. So which means definitely your car will be better than the other car because the other car road is smaller compared to the road that you're using. Okay, but what I'm trying to say is when you try to race, you need to make sure all the condition is the same and the problem that they use to test the algorithm has to be on the same level. Okay. And then also when you try to formulate your problems, make sure that the problem is not artificial. Okay, what I'm trying to say is like you need to make sure that whatever you use to test your algorithms, make sure that actually is based on a real world usage. Okay, don't try to use an oversimplified problem domain. For example, you try to say, okay, for a sensor network, you might want to say, I want to just test it in a very non-noisy environment. But in real life, you usually implement those kind of a sensor network in a noisy environments. Or maybe you might have tested your result based on a certain number of inputs. So in other words, your testing data is not sufficient. Okay, so that's the three things that you need to make sure that when you want to do your hypothesis test, when you conduct when you design your experiments, make sure that you test your algorithms multiple times, and also make sure that you compare the algorithms using the same problem. Okay, I mean the testing environment is the same, and also finally you make sure that the parameters that is on the environments is actually as real as possible. Okay, so which means you need to make sure you have when you test your software, let's say in the software engineering perspective, you want to make sure when you test your software, all the test case data is you use actually different test case, not just particular test case data. Okay. So the other issue, one issue with hypothesis tests is usually there's a lack of rejection of null hypothesis. Okay. Because what happens is when you reject null hypothesis, it doesn't imply that you already proved null hypothesis. For example, when you saw, okay, the null hypothesis is all swan is white. Suddenly you say you saw a white swan. Then you say, okay, this is a white swan. All swan should be white color then. But if I reverse that the other way around, if I observe all swan is white, and this one is white, how you can actually determine that? How can you actually show that? Okay, so in other words, if you prove that, if you reject my hypothesis, it doesn't mean that the opposite is correct. Okay. So for example, another example is, for example, when you have null hypothesis showing that, okay, there's no effect of detections, which means that you don't observe any effect. So which means that, and I saw these samples and null hypothesis work. So, but if I reverse the other way around, if I turn it the other way around, okay, does the null hypothesis always hold when I see does all these samples usually hold when your null hypothesis actually is always valid? So you can't, I mean, those numbers you can't actually calculate. You can't actually calculate it, but you need to use Bayes theorems to actually to work this out. Okay. So what particularly I'm trying to say is when you accept your null hypothesis, it's fine. But when you reject your null hypothesis, you cannot say that there's an effect on your data. Okay. There's an effect on your detections. But what you can only prove from your null hypothesis is saying you cannot say you cannot accept that there's a fact that there's no effect on the detections. Okay, but you cannot say there's an effect on the detections. But you cannot do the other way around. Okay. So once you do all your statistics, all your null hypothesis, you formulate your null hypothesis. So what can you do with your data? What can you do with your results? Okay. Once you have formulated your null hypothesis, the next thing is you need to analyze your results. And what you're going to do is you're going to use statistics to do that. So statistics, by definition, is a summary of data. A summary is a summary value that actually capture the properties of the characteristic of the data. So what happens is when you run your experiments, usually you have some sort of data that you're going to collect. Okay, so your data can be defined into different types. It can be you can actually collect your data based on the different mode of the data. And then when you want to analyze your data, you can actually use median, you do the quartile, okay? Or you might want to calculate the means. So all these, the type of data, the property of the data that you have is, for example, the mode, the medians, and the means, actually captures the characteristics of the data here. Okay? And the statistics that you want to use in your experiments or in your research what you need to calculate here will actually depends on the data that you use or the data that you have. Okay. So which means, in other words, when you do your experiments, should you represent your data in means and standard deviations, or you want to calculate your data based on median and quartile? And whether you use a median or use a mean will actually depends on the type of the data. So there are three band category type of data that you can use in your research. So the first type, we call it the nominal data or the categorical data. So this type of nominal data is a data group in category. For example, you have your on and off, okay, in a 1 or 0, for example, in binary, or you can have a male and female, or you can have English, you can have a type, for example, you can have a category like English, maths, or you can even have a red, blue, and yellow. Those kind of that's usually a category data. So what happens when you want to do the operations on the type of the data here? Usually you try to do the equality of category. Okay. So in other words, the type of statistical data mode that you're going to use here is based on the mode. Okay. So in other words, when you try to plot your graph here, there's no point that you plot your graph in a dotted, and then you join the dot together. So if you have this kind of data, nominal or categorical kind of data, it's usually good to present your data in some sort of like a bar chart here. Okay. And what usually you have, present your data in a table format, and you plot your graph. And usually when you plot your graph, you try to use a bar chart when you have a category or nominal data. The other type of data that you usually find in your research is maybe a data that can be ranked. Okay. So data sometimes that can be ranked. For example, if A is greater than B, B is greater than C, or you might have a data like very good, very bad, and very good, a very bad, neutral, good, and very good data. Okay. Usually the operations that you want to do, you want to do some comparisons of the rank. Okay. And in this case, numbers are usually used to encode the ranking. But which means, in other words, you might need to use the numbers itself, and it makes no sense to actually calculate these numbers. In other words, there's no point you draw the means or you join the dots of the graph. Okay, so the encoding methods will be just be based on the so in other words, if you want to, the encoded method will be just based on whatever you saw on the data itself. So in other words, bad, very bad, neutral, good, and very good. So in this kind of cases, when you have your data, so for example, there are 20 with a data A, you actually have 27, 51, 10, 8, 3, and 1, and you're actually comparing between A, B, C, D, E. So you might as well try to plot your graph, use a bar chart. Okay, so in other words, there's no point you join as a graph as well. Okay, so the last two types of data is known as the numerical data. So this kind of numerical data is the data that you usually use in your research as well. Okay, the previous one is more related to when you do some sort of a survey kind of a research, but this one is more to do with when you do a lot of data collections, readings, when you do your test run. Okay, so there are two types of data that typically used as a numerical data, whether you have an interval data or you have a numerical data. Okay, so numerical interval are actually numerical data with some arbitrary 0 points. So in other words, like a temperature for example, like temperature in degrees Celsius. There actually is the 0 there doesn't actually represent a 0, but it's actually is an arbitrary 0 point. Okay, so in other words, you need to be careful when you use a arbitrary 0 points. So for example, a typical newspaper report that you might see is, for example, is like, okay, when measuring the temperature in Celsius, the newspaper will usually report like the temperature rises by 1 degree Celsius. Okay, so but that 1 degree Celsius doesn't mean that it's actually increased by 1. If you convert it to Fahrenheit, it's actually increased by different value. Okay, because as you know, the calculation, based on the calculation of Fahrenheit to Celsius, there's some sort of calculations. So Celsius itself is not 1-to-1 mapping, which means that if a temperature rose by 1 degree Celsius, it doesn't mean that the temperature rose by 30. In Fahrenheit is 34 degrees Fahrenheit. Okay, so you need to be careful when you have some sort of arbitrary points. So the type of operation you usually do in interval is actually you can usually try to compare the values. Okay, and what usually you do some sort of operations, you do some sort of arithmetic for operations like additions, subtractions, and typically intervals you might want to use, commonly used in the research, is to calculate the means. Okay, the statistical characteristic you might see, maybe the means, the standard deviations, i.e. the spread of your distribution of your data, or even the skewness of your data, the distribution itself. Okay. And the third one, this last one is the ratio data. Ratio data is actually is the reverse of the interval data, where it's actually is a numerical data with an absolute 0 point. So in other words, the value actually start from 0. Okay. So for example, temperature in kelvins, the length, the mass, okay, the lifetimes, and so on. So the typical operations is you can actually do arithmetics up to multiplications and divisions. And again, the statistic here is similar to the interval. You can actually find the means, the standard deviations, the spread, the skew. Okay. And for the differences between ratio and interval is the ratio in variables never fell below 0. 0 will actually mean it's 0. Okay. So when you talk about means and standard deviations, so how you actually calculate the means and standard deviations is basically you take the sum of all your distributions, and then you divide by the number of distributions you have in your data sets. So it's basically when you calculate the means, is items with average values, and when you try to do the means, calculate the means, is actually trying to measure the centrality of your distribution itself. Okay. So for example, when you have data sets of a means of -30, 1, 2, 3, and 4, okay, that actually means when you calculate this means actually give you a -4. Okay, but when you have a 0 here, 1, 0, 1, 2, 3, your means actually become 2. So it's actually try to the values. I mean, means actually try to measure the center of your data. Okay. So for this case, for the first means here, the center of data actually is at -4. Okay. And the typical standard deviations, when you try to calculate standard deviations, actually you try to find the sum of the value of I to n, okay, based on the value of the means here, okay, based on the means that you calculated, you divided by the n minus 1 itself. That will actually give you the standard deviations. So because it's derived from the estimated sample means, it would means that it would need, which means your n would need to be use the populations of the mean itself. Okay, and this particular measurements actually give the measurements of the spread of your value. In other words, how your value actually spread across your data, the spread of your value within your distributions. So for example, when you have a standard, when you have the same data set that you calculated above here, the S standard deviation produced here actually give you a 14.6, and the standard deviation give you actually 1.6 here. So if you compare between these two data, you actually know that, okay, this data, to use means and standard deviation to present these two data sets, it is better to, it actually give a better representation if you use on this data compared to the other data. So which means that, is it always good to present your data in means and also using a standard deviations? So to answer that questions, I would say that, okay, means is good. To use mean and standard deviation is good on this data, but it doesn't show, I mean, it's not really good in showing this data. Because what happens is, when you have a means of -4, it doesn't show much about how your spread of your data is actually look like. Because when you present your result as a -4 plus -6, 14.6, okay, for one sample, and the other sample, let's say 2 minus, I mean, another sample, let's show a means of a a means of another sample set, let's say 2 and 16. You might say that, okay, sometimes, because this is a negative value, but you bring this a negative big value, you actually show that this actually have a better means compared to a higher means. But that doesn't mean that this result is better than that. I'll show you more example later on when I talk about which is the best approach. So when you try to look at this particular example here, you have a positive variables means of 1.69 and standard deviations of 1.14. Okay, so when you try to use mean and standard deviations to plot this particular set of data set here, okay, you actually find your means is actually here. Your means is actually produced is actually around this area. Okay, so what you're trying to say is, okay, your data spread is along this area, but you actually fail to capture this side of the data sets. Why this happens is because your data is skewed toward the left. Okay, this is because the majority of this happens also because the majority of the data is actually greater than your means. Okay, so when you try to plot your data using means and standard deviations, you cannot actually detect skewness of the data. You don't actually know the characteristic of the distribution set that you have, the distribution of data that you have, the set of data that you have. Okay, so which means you can't detect skew, whether your data is skew or not. And what's come to worse is sometimes the means minus your standard deviation could be even outside the range of your data. When you have enough data, you might actually realize that, okay, whatever you shown in your means and standard deviations doesn't actually represent much about your data sets. So I would say that when you're trying to present your data, or you're trying to understand the data, the sample data that you have, whether you want to use mean or standard deviations, you have to be careful of it. So another approach which is better to represent your data is based on means, median, and quartile. Okay, median and quartile are usually much better. Okay, and for me, I usually prefer to use median and quartile, because what happens, median usually give you the sample size based on you usually try to show the distribution of the sample based on items with an average range. Okay, so it's basically is a non-parametric measures of centrality. Okay, so how does median work is actually you try to rank all the items in order and then choose the midpoint of the data sets. Okay, so when you have this set, when I use the same data set now, you can actually show that, okay, I have -30, I have 1, I have 2, I have 3, I have 4. And so the midpoint now is, instead of -4 that we have earlier, now actually I move your central towards really to the center of the data, which is basically 2. And for the second case, the median also show a 2. So which, when you use this kind of a median approach, is actually less affected by your outliers. Okay. So in rank, when you use a median approach, rank is what is more important, not the value itself. And then how you actually, the other things that you usually use with median here, when you want to use a median, you also try to measure the quartiles. Quartile will shows you the spread of your data. Okay, your data sets, your data that you collected. And it's usually based on a non-parametric approach. Okay. So you can actually see when you can actually detect skewness when you see there's a differences between the quartiles. Okay, and typically when you calculate your quartiles and your median are usually based on the 50 percentiles. Okay, and your quartile is based on the 25 and 75 percentiles. So we're using the same data again this time. Okay, we use the same data, plot the same graph. This time I'm trying to show the means. I'm trying to use median and quartile to represent the data set that I showed you earlier. Okay, so this time the median is 0.98. The first quartile is 0.34. Okay, and the last quartile is, and the third quartile is 2.332, and this is 0.34. So that actually show a better spread of your data here. And then usually what you do, you can actually see that the median actually move towards the median actually shows towards the first quartile. What this means actually, it shows that your distribution of data sets is actually going these directions. So it actually shows your graph is skewed. Okay. So this actually shows much better representations. So in other words, when you plot this particular median and a quartile range, interquartile range, actually it shows that the half of the data is less than the median. Okay. So the quartile also help you to indicate the skewness of your data sets. And the quartiles itself is actually within the data range. So what happens here, you might want to have your interquartile range here. And there's a few things that you can do here. You can also set a barrier, a limit, okay, between your certain level after your quartile here to detect outliers. So you might want to set a barrier saying that anything beyond 4 or anything beyond 5 here, based on a particular formula, okay, all the remaining data of sitting here is actually can be ignored because it could be outliers. Okay. So when you're trying to compare means and median data, okay, usually most experiments or most paper that you read in research, usually you try to think about data are usually numerical, and most of the data sets when you collect, usually you try to say data the data that you collected are usually normal. When I mean normal distributions are which your data set is actually a bell curve, exhibiting a bell curve. Okay, so but in real world data, when you collected, not all data are normal distributed. Okay, i.e. not all the data sample that you collected are normal distributions. In other words, it doesn't exhibit a normal distributions properties. So which means that when your data are not normal, it is much more better to use a median compared to means. So in other words, means and standard deviation will only work for normal distributions. When you have data set that actually is skewed to the left, like this one, okay, it is better to represent your data in median and quartile. Because if you look at the example between these two, the first graph here, I mean the means here actually shows that, okay, your data sets is actually showing a normal distribution. When I mean normal distribution, it's actually showing you going up and then you're going down here. Okay, but for this one, because this one is actually the median always show the central. When you plot the graph up, you try to draw the graph, it's actually show a slowness here. So it's actually indicate your data actually skewed to the left. Okay, so it actually shows there's a skewness of your data. So median is usually much better median and quartile approach is usually much better than means when you have a lot of data samples that you can actually want to represent. Okay. So when you're trying to, and non-normal distributions such as median and quartiles are usually affected by outliers. Okay, so outliers, in other words, long tail usually dominates by the means. The earlier example I showed you, usually there's a long tail towards it. So which means when you have long tail data on this graph here, whatever you calculate on the standard deviation here doesn't mean doesn't hold anymore. Okay, because when you draw your graph, standard deviations, you know that is usually when you calculate you're usually interested in 0.05 and 0.05 here. But when you have a skew data, standard deviations doesn't actually tell you much. Okay, it might actually mislead your result itself. So if you use the assumptions you do in experiments, usually you're trying to say the underlying distributions are usually normal. And as I said earlier, most distribution that you get are not normal, and it's not always normal. Okay? And also, most of the statistical tests that you use, for example, like your t-test, will require your data to be normal distributions. So in other, if you use a t-test on the non-normal data distribution sets, then your statistical test output will not be valid anymore. Okay, so which means you need to use other tests. But if you have a non-parametric approach, usually you doesn't need to worry about the statistical test that you use to test your data. Okay. So why usually people assume normality? Because normal distribution are usually relatively common. Okay. This is due to the central limit theorems, which in other words, when you have enough of data collections, you can actually, when you collect enough sample, enough data size, enough data number of data size, usually you can think that your data is normal distributions. But does it always the case? You just make the assumption saying that, okay, if I have 100 data sets, 100 data points I've collected, I can assume that the data is normal distributions. But however, there's sometimes your data might give a long tail distributions, okay? And also there's also some other data samples that may actually come up not just very common. For example, long tail distributions, the power law, the skew data, all those are very common. It always happens in your data collections. And also before computers, statistics are usually considered as an area of research. So because you have statistics, you can actually use statistics to produce very elegant statistical results for normal distributions. That's why people are usually so used to normal distributions. They try to say, okay, when I have enough data, you can actually produce data that you can actually produce a data distributions that actually are usually normal. Okay, and there's very little that you can do without those assumptions, because what happened during that time, there's no computers. You can't actually collect a lot of data. Okay. So what usually you do, you also try to tabulate the results, and the table usually depends on the distributions. But with today's computer system, okay, with the computer processing in availability, you can actually analyze the actual distributions rather than just approximate it. Okay. So because of that as well, the rise of non-parametric statistics is happening now. Okay, so which means that non-parametric tests should be your default choice. Why we prefer non-parametric tests? Because if you use parametric tests like t-tests, then you need to be able to show that your distribution is normal. Which means before you can do a parametric test, you might need to use t-tests to test your data whether it's normal or not before you use the t-test to compare between two distributions. Okay, so you might do the test double. First, you test whether your data is normal, have a normal distributions, and then you can compare compare your data with the other data. If the other data is showing also normal distributions. Okay. So technically, it's less powerful in a way because for non-parametric statistics to work, you need more sample to be able to get a significant value. But however, it's not that much more. For example, for a 100 rank sum test, which is a non-parameter approach, you need 100 rank sum tests compared to a 95 ranks a t-test. So in other words, you need additional 5% more run to get the same accuracy. Okay. And then because this criticism is only relevant for normal distributions. So in other words, if you use a non-parametric statistics on the normal distributions, it is basically less powerful. But yet, it's not that significant less as well. Okay. So once you actually know the type of the data that you want to use, the next thing is you're going to use statistics. You need to decide what sort of test you want to perform on your data. Okay. So assume that you have three samples that are drawn from the same population here. Okay. So when you try to look into these three sample sets, how do you know that these three data samples are actually drawn from the same distributions? Instead, by looking at it, you can say, okay, because the data is actually accumulated around this area and this and that is the same distributions. And how about this one? I can say, okay, I have this another test now. I have these three samples here, and I claim that these three samples are actually drawn from different populations. But again, how can you tell? By looking at the graph here, say, okay, the graph is, you have your central here, you have spread, and then this is central here, but the spread here is bigger, so it is different. So blue is different from red. And this is, I can say it's the same because they're so close, but I can't just put on my paper saying, okay, these three coming out from the same population without doing any statistical tests. Okay, so there's a need to actually, besides plotting the graph, looking at the graph itself, you need to, or even you have your mean and average, you can actually say, okay, this result is actually different. Okay, so what usually you do is you come up with your null hypothesis earlier. Okay, with saying that the sample that you have, X and Y, are actually drawn from the same populations. Okay, so which means when you talk about null hypothesis, the sample X and Y are drawn from the same populations, you're trying to say is they have the same statistical properties, i.e. they have the same median and the same quartiles. However, most of the statistical tests that you're actually trying to test your data samples is actually required the distributions to be normal. But usually it's not the case. As I shown here, it could be skewed to the left, it can skew to the right. So when the under distribution is not normal or even unknown, i.e. you didn't test your data distributions, it's better for you to use non-parametric tests straight away. Okay. So when you want to talk about non-parametric tests, usually what they do is trying to compare whether the median is different or not. Okay. So there are a few non-parametric rank sum non-parametric tests, for example, the rank sum test, which also known as the Wilkinson's and Mann-Whitley test, which is used to calculate the probability P that the two samples are drawn from the populations with the same median. Okay, so instead of using the mean, you actually try to do the test based on the median. So in Matlab, usually you try to run the test using a rank sum bracket, your first data sets, your second data sets, and the alpha value you're interested is actually 0.05. Okay, so if the P value that you receive or you calculated is less than 0.05, you can actually reject the null hypothesis at a 95% confidence level, because what you can say is the median are actually different. Okay, which means the median is not the same. And also remember, if P is greater than 0.05, it doesn't mean that I will accept the null hypothesis. Okay. So this is one typical example where you have a rank sum test. So on just now the same data sets, 1, 2, 3. Okay. So when you try to look into it, we are looking at 0.05. Okay. So for the same test, you realize that all of these value actually give greater than 0.05. When you compare to the other one, okay, so you realize that, okay, you have a 50 sample sets. These sample sets also you can't reject the null hypothesis. But for this one, you can actually say these two set of data actually you can reject your null hypothesis, which means the median is different. And even better, when you run more data sets, you actually shows that all the data sets is actually different. Okay, so because the median is different. So if one thing that you can see, the more experiments you run, the better, the more accurate your result you might get. Okay. So how can you actually show the two distributions are different? If you can't show that the medians are different, you can actually use non-parametric KS tests to show the calculated probabilities from the two samples drawn, okay, from the populations have the same distributions. So besides using the rank sum test, you can also do compare the distributions. The first one actually compare the means, like the median. So if you can't see the median is different, another test you can do is actually you want to see the distributions, whether the data sample have a different distributions or not. Okay. So again, the null hypothesis that you define here is the distribution X and Y has the same distributions. And you run your test in KS. If P give you less than 0.05, you can actually reject your null hypothesis at 95% confidence level. Okay. And because the distributions are different in some way, okay, whether by the median or by the quartiles or by any other ways. So you don't know what is actually different. This one, you shouldn't say the median is different, but you can actually say the distributions of the data is different. Okay. So now you do this KS test now. So on the same data sets that we have earlier, okay. Now you realize that, okay, using a KS test, I can actually show that the blue and red always can actually shows that the distributions is different. Okay. And when you have more data, everyone actually shows that the distribution of the data is different, which actually is true. You compare to these two, the distribution of the data is quite the same, but this one is definitely different. And the same as this one, all these three is actually different, and this is even show more differences. Okay. So going further, you can actually use rank sum and KS tests to test if the two samples have a different distributions. Okay. So for example, you want to test whether the results that you from lots of runs from one algorithms are statistically different from the results from lots of runs from another algorithms. Okay. And then there's also other tests, like for example your pair data test. Okay, which means you're trying to do a test of data before and after, or to test whether a change actually have significant effect or not. A change of your algorithms, for example, a change in your parameters have any significant difference on your algorithms or not. Okay, on your results. So when you try to decide what statistical test you want to do, you try to decide based on what your null hypothesis is. Okay, and then you also need to decide on your null hypothesis and how you're going to test it before you generate the data. So in other words, once you formulate your null hypothesis, you need to make sure that you need to think about how you're going to test your null hypothesis, then try to generate the data based on the null hypothesis. Then you can use the test that you think that is suitable to your null hypothesis test as well. Okay. So another thing that is important as well is you need to get the raw data. Okay. Or you need to perform all these tests. You need to have a raw data, not just a summary statistics. So in other words, if someone give you a data, just give you the means, you can't actually understand the distribution of the data by using data with the means. Okay, which means you need the raw data sets. And the other things that you need to think is how can you actually perform a significant test that yours is better than theirs if you don't have your data. You need to have your data. For example, when you read a paper, the paper actually describes the experiments. I do this, I set the parameters to be X, the parameter to be Y. And so you think, okay, maybe I can just run the same thing from the paper, but you might not get the same results because what happened is they might be using a different data than what you have. They didn't share the data. Or you might think about, you want people to test your experiments with your algorithms, but if you don't give them raw data, they can't actually do. So in other words, nowadays, if you try to look at most research papers, people are usually trying to share their raw data. And some of the raw data they give you maybe is in the GitHub. And sometimes they also give you the code. Okay, so it's a good practice as a researcher to actually share your data and also your source code. Okay. So another things that you need to look into is as well as a null hypothesis. So if your algorithm is different from another one, you can definitely detect differences. Okay. When you develop a new algorithm, definitely there's a differences from another people using statistical tests and based on a null hypothesis. However, you need to make sure that you have enough sample data to test your algorithms. When you have, even if you have you have a lot of data sets, you definitely can find a better statistical significance when you test your data sets. Okay. So, and traditionally, when you don't have, especially in medical research, you can't usually what they test your research actually depends on the test on mice, and usually mice are expensive, computer are cheap. So you can actually do a lot of tests using computer, collect a lot of data, run the simulation repeatedly, so that you can actually get a lot of sample size up to a level of thousands. Okay, so your statistical test will be affected by your data sample size. The other thing that we might look into it is whether when you test your statistical test, you find your data site, the data distribution is actually significant. But is it actually important? Okay, even though let's say, okay, I find no differences, yeah, mine is better than the other one, the statistical tests show that it is good. But is it really good? And but the new case is usually not necessary. You can actually nearly get a statistical significance result by just having enough sample data size, just like the earlier example. Okay, I have more data size, I have more data, like this one, I have more data, I can actually show that my result is more significant. Okay, because this is running on the same algorithms, I mean on the same formula in Matlab, and I increase the data samples, it actually shows that the results are significant. But is it really important? Okay, it might not be as important as, it might not be an important difference. There might be some difference, but the difference is not important. Okay, so you do also need to find a way to show that whatever significant difference that you tested on your data, you need to show whether the distributions are really different. Okay, because sometimes the two distributions that you tested on your statistical test can still be very similar, although your initial test show that it is different. So in other words, one of the things that you need to do is to measure the effect size. Okay, so the effect size actually gives you the measure of importance, i.e. is scientifically significant. What we have done earlier is more like statistical significance. Now we are talking about scientifically significance. Okay, so this is one good example. Is, for example, you might do a test. This graph here might show that these two distributions are statistically significant, but it is not scientifically significant because it has a very small effect size. Okay, this is a median effect size. Okay, you can see the spread between those two data, the separation between the data is quite big. And this one is actually show a good big effect size. So in other words, I can definitely confidently say this data sets here has a higher effect size, and it actually shows me this data, these two algorithms are actually really different. Okay, and the difference are actually significant. So how can you actually do the effect size test? You can actually do the measures based on a rank sum test here. Okay, calculate the rank size, rank sum, use the same rank sum, and then you calculate the value of the maximum size of M, and then you use this formula here to calculate the measures. So measure actually gives you the measure of importance, Okay, so A lies the A value you calculated is actually lies between 0 and 1. So if A is less than 0, okay, you actually use 1 minus A in the test. So when it is 0.05, if it's 0.5, it means that the median is the same. When 0.06 is the means the effect is small, and then as it get bigger, which means it's have a bigger effect size. So usually you want to highlight on the red, the blue part of the data sets here. Okay. So when you look at this one, okay, all this data distribution show that okay, there's a differences, but in terms of the importance of it, it's not that critical because there's there's only 0.05 here. Okay, and this might shows that there's some has a bigger effect. Okay, so this data set actually show is much better than compared to this data sets here. Okay, so the last part is about the graph. So once you have calculated, presented your data in tabulated and in the t-test, the last thing you want to present your graph. How you present your graph? You know that there's a lot of different ways that you can actually present your graph in Excel. Okay, you can have your bar chart, you can have your even 3D graph and this and that. And I've seen people, I mean, this graph has been widely used in management, but in research, you might not see it used very frequently. For example, this graph here is a 3D, but you can't actually really read the actual value of it. So for example, there's this particular representation as well, A, B, C, D, E. If you ask me which is the best representations, or like if I ask you which is the representations, you can actually try to answer this for me, and I'll tell you the answer when I finish off this particular part of the lectures. Okay. Or you can put in the chat group to answer which one do you think is a better graph? Better representation, A, B, C, D, or E, or F. Okay. But I would say don't choose D, because D definitely is the worst of all. I'll call it is a rubbish. Okay, and B is also rubbish. It doesn't actually tell me much at all. Okay. So the other things that you want. So when you try to plot show your data, you need to plot your data to expose its structure. Now you try to show how does the whole distribution of the data set look like. Okay, for example, this one. So it actually shows that the data set actually changes here. And then it also shows that there's differences here as well. Okay, usually you want to understand the characteristics. You're trying to expose the structures. So when people look at your papers, they put your graph. They say, okay, so the algorithms actually show some trend. There's some trend exhibiting your plot here. And the other thing you need to look on your data set is actually for outliers. Okay, so sometimes you might have data that actually have some anomalous data. I would say error data, but the data set that actually doesn't fit within your distributions here. So you cannot just ignore this data here. You might want to understand why it happens. Is it just a statistical fluctuations? Or does it just happens once in a blue moon, the 6 sigma outliers? Or is this errors in your experimental design or implementations? If it is, try to fix the problem and rerun the experiment. You try to get rid of these outliers as much as you can. Okay, and maybe it could be just an interesting new finding that you want that allows you to do your research further. Okay, so as I say, this rather than you used to plot your means, this is the approach that you can actually plot your non-parametric data using a box whiskers. Box whiskers actually shows the means in the upper and the lower quartiles, and then you can actually calculate your maximum data values and your minimum data values here. Okay, so anything outside this tail here will represent an outliers. Okay, so in a box plot, you can further improve your box plot by having a data cutoff value. So anything above the cutoff, as I say, is just the outliers. Okay, so a typical outliers you calculate is actually based on 1.5 times 1. The interquartile range. So what is the interquartile range? It's actually the differences between the upper quartiles and the lower quartiles. And you multiply by 1.5 will give you the maximum and the minimum. Okay, of the cutoff point. And then you can add on to it your upper limit and your lower limit to find your cutoff. and your upper limit 2 is your cutoff here. So anything outside here can be considered as a outliers. Okay. So another way that you people might plot is actually to include your means in your graph as well. Okay. So for example, this also shows the means. So with this, you can actually show whether your means and median is actually similar or not, very close together or not. Okay. So it's a good idea to actually show your means and use your median and show your quartiles. So how you actually plot your box plot using Matlab? Okay, you can actually use the xrand. Okay, you can actually use the box plot command and then just plot it out directly. Okay, and in Excel also you can actually do your box plot. And how you do box plot in Excel, I can't remember the formula, but you can actually definitely use box plot in Excel as well. If I found the link, I'll let you know. Okay. So with that, you can actually plot all the graph. And now, how does the whole thing fit into your research? How can you actually use the whole thing? So this is one of the framework that I actually created to actually do your research based on the case study that we talked earlier. Okay. So we propose an experimental verifying process where you try to evaluate the result obtained from your experiments, both hardware and software, to validate your routing protocol. Okay, you remember the earlier problem? I'm trying to evaluate the routing protocol for wireless access network. So what happens is usually you try to use all the statistical approach that I described earlier, your hypothesis test, your formulating of your hypothesis, and then do your experiments. So what usually you do, the steps involved will be you set your objective and formalize your hypothesis here. Okay, and then you design your experiments. In other words, you need to decide how many runs you need to do. You set your test scenario, and then you determine your error evaluation methods and your metrics. And then you apply the framework based on what we call the conceptual statistical framework, which I'll show you later, to test to analyze the result, the data that you collected. Okay. So I'll skip this page because I think my time is almost over. Okay. So this page actually talk about the problem that I'm trying to investigate here. Okay, when you talk about wireless access network, you know wireless access network is usually very unreliable. Okay, and people usually use simulations. So what I'm proposing here, besides using simulations, you also need to do hardware. But I don't want to run the hardware too much because hardware usually costs a lot of money. So how can I combine both hardware and software simulations to show that both the algorithm I propose will work on the hardware when you implement in the real world. Okay. So this is the algorithm that I propose. You have these algorithms called a multi-model where you actually allow the nodes to decide which routing protocol to use. Okay. And after that, I'll define the experimental objective. Okay. So the objective is trying to demonstrate that my algorithm have a better network reliability and also lower latency than the other algorithms. And then here is my hypothesis. So there's 4 hypotheses I actually defined in my experiments or in my research. So first one, I said there's no significant improvements in the packet delivery rate. There's no significance in the latency. There's the total of routing protocol generated by my algorithms is no difference. And there's no difference between hardware and simulations. So you actually see all my 9 hypotheses here is actually talking about no differences. Okay. And then the conceptual framework actually consists of this particular approach here. You actually collect your data using protocol A, and then the hardware using protocol A, the simulator and hardware. So usually simulated you have more runs, and the hardware you have a less run. Okay, and simulated you have more runs, and hardware you have less run. And then after that, you can do your first statistical significant test. And what I'm using here is actually use a non-parametric Mann-Whitley Wilkinson test to detect the difference in the median. Okay, the same case as this one, I do the same test, statistical significant test for protocol on hardware. And then second test I do is actually I do a scientific significant test, which is the air test. And then finally, I do a third more test to actually to compare the similarity between the hardware and the software. Okay, so this particular approach is that this framework can actually use in most scenario when you have both hardware and a real world data versus and when you also have your simulated data. Okay, and you can compare your real world data and your simulated data, whether it's the same or not. Again, you also compare with another methods. So method A, method B in real world, method A in simulated environments, method A and method B in real world environments, and you can actually perform using this framework based on the statistical approach that I discussed earlier. Okay, this is just basically the experimental design for the hardware and the software. And then this slide actually I tried to describe the evaluations methods. So I calculate the means and medians, the box whiskers for the packet delivery rate, the average delay, the routing overhead, which is the three things that I'm trying to prove here. Routing overhead, latency, and the packet delivery rate. Okay. And then apply the conceptual network on 15 data sets from hardware and 35 simulation runs, okay, from the simulator. So this is the result that I plot on my graph here. Okay, you can see that I plot the median and there's a mean here, and you can see that both the hardware and software here is actually exhibit very different distributions. But what is important here, actually, I'm comparing the three different algorithms here. Okay, so you can and you can see that algorithms, which is indicated by the green color one. Okay, when you have a small failures and as failures increases, you can see that the green actually tolerate better. Okay, even though it has a lower means, but the spread of the data is better. And this one actually shows the p-value, the statistical significant test, and the scientifically significant test here. Okay, for both hardware and software here. Okay? And you usually try to plot your graph as much as you can here. And then the last one is your similarity test, whether your goodness or fitness test to show whether the hardware is the same with the simulation or not. So out of 45 tests, only 4 actually show some similarity tests. So which means I need to do more tests. I need to improve my experiments because maybe the configurations used in the simulations are different from the actual real world, especially when you talk about the radial model. Okay. So once you finish off, you can actually do your conclusions for your experiments, and then you can actually conclude your work there. So the takeaway questions here, you're going to from these presentations, you need to make sure that you make your research actually significant. And how you do that? First thing is you make sure that you present your full data sets. I mean, you present your full data distributions. Okay. Show how your data is spread across the data that you have. Again, use median and quartile. Plot your graph, okay, using errors bars. Also box plot. Might as well use both as well. You might as well present both errors bar and a box plot. Because errors bar actually shows you the means and the standard deviations. Box plot actually shows you the median and the skewness of the data. Okay. And also try to perform statistical significant tests to detect the confidence level, and also perform the scientific significant test as well. And last and not the least, share your data, and also even better, share your coding itself. But usually when you want to use people data and people coding, make sure you cite their data as well, because you don't just use people data without citations. But I'm not going to cover citations here because I think you might have some other talk that actually related to citations. So this is some of the takeaway reading that you can actually bring with you. So with that, I can end my presentations. Thank you. If you have any questions, we can actually talk about the question and answer sessions next. And this is just my university, just do a bit of publicity on our university. So one of our visions of UTB is actually to become a global university impacting society. Okay, and we actually very try to cultivate our students to be innovative, industrial relevance, as well as have all those NIV values as well. Okay, thank you. hand over to Doctor.
Okay. Thank you very much, Dr. Lim, for the interesting presentation. Thank you for sharing your experience and expertise regarding this topic. The explanation is very thorough, from data and statistics to visualization and how to integrate it all in a research framework. Thanks. And now we enter the question and answer session. I will invite the participants. If you want to ask a question to Dr. Lim directly, you can use the raise hand button. In addition, participant can also ask question via chat or by using the Google Form. Okay, while waiting if there is any participant who want to ask question directly, I will read some question from the chat room and Google Form. The first question is from Mrs. Fanny Juanita from ITS. The question is, what is the best graph to show historical data so that it can explain the background of the research clearly?
Okay, what is the best graph to show historical data? So the best approach when you have historical data and current data is to actually, the first question is, does the historical data and the current data come from the same experiments or not? Okay, if it is the same, the first thing you might want to do is to plot everything. Plot everything first, which actually shows you how the trend of the data sets, i.e. starting from, let's say, historical, starting from year 2000 until 2020. Okay, so it actually shows you the trend, how year 2020 changes to year 2020, from year 2000 to year 2020, how the whole data set changes. Then once you understand the trend of the data sets, then you might want to also measure whether the changes is significant or not. Okay, so when you might want to plot, go down to comparing year by year, okay, or month by month, or week by week. So this question here is more like saying, to answer your questions, it all depends what you're trying to understand from your historical data and your new data, if you understand what I mean. I might have cancer data sets from year 2000 to year 2000 to now. But what are you interested in? How the cancer has changed from 2000 to 2020? If you want to see the changes, then you might as well plot the whole thing. If you want to see whether there's any differences or not, you might want to do, if you're interested in to see every year how the thing changed, then you might want to plot year by year. If you're more interested in how it changed every month, then you might want to plot month by month. But again, if you plot month by month, you might want to show you might not just plot by calculating the average and show the average. You might want to use a box plot to show every month how the data change. Because what happens when you plot the monthly data, you actually calculating the distributions of the data sets for that month. Okay, so what I would say is you might want to plot the box plot for every month, or every week, or every day, or every year. Depends what you're trying to show.
Okay, thank you very much, Dr. Lim, for the answer, and thank you, Mrs. Fanny Juanita, for the question. I think the answer is quite clear that for historical data, I think the most important thing is the time unit to show the importance of the data, right, Dr. Lim?
Yeah, true. But the thing is also what you're trying to understand from that data.
Yeah.
You need to understand what you want to understand from that data. Then you can actually know, okay, how can I use this data? Because a lot of historical data is important, but how you want to use it for? What are you trying to analyze?
Okay, thank you. The purpose is the most important thing.
Yeah.
Okay. For the second question is from Mrs. Safika from University Teknologi Mara, Malaysia. The question is, what if the data, my data, are normally distributed, based on the skewness, kurtosis, and Shapiro wheel, but have unequal variance when tested for homogeneity of variance. Can she use mean and standard deviation to report the data? And is it correct? Is it a correct step to opt for Gibbs-Howell test in the post-hoc test instead of 2K test? 2K test. Thank you.
Okay, so the first thing you know, I mean, the first thing is, as I say, you claim your data is normal. Okay, so in order to claim your data to be normal, first thing you need to test to just do a proof that your data is normal using a particular test first. Then once you test your data is normal, then you can actually use the test that you, I mean, whatever test that are usually suitable for normal data, right? So to answer your questions, yes, you can do that provided your data is actually normal. When I mean normal, it's like
if the data have the data have unequal variance for when test for homogeneity of variance. What if the data have unequal variance?
Unequal variance. Yeah, that's the thing. That's why I say is that you might want to test your data for normality first, and then try to when, I mean, the thing is, then you can do the unequal variance test. If unequal variance test, then it's just your data to be that way. There's nothing much you can do, isn't it? Unless you want to modify your data.
Okay. Okay, thank you very much for the answer, Dr. Lim. Yeah, that's the data. Okay,
And the method and the method that she was talking about, I'm not really familiar with that method, but the thing is, as long as that method is suitable for normal data tests, I mean for normalized data, then you can go ahead and use it. Or else you might want to find other methods to test it.
Okay.
Yeah.
Okay. So it's okay if we want to normalize the data, right?
Yeah.
Okay, thank you very much, Dr. Lim, for that answer. And then there is also a question, maybe it's rather general, from Mr. Haris from UITM. If we are dealing with existing method throughout our research, what is your advice for this situation to avoid if we are dealing with existing method? What is your advice? Yeah, to avoid duplication or plagiarism.
Yeah, okay. In other words, you're trying to repeat some other people experiments, right? If you ask me?
I think the question is about we have an idea and then we run it, and then halfway through the research, we find that someone already published the same research. Yeah, the same idea.
Okay. If that's the case, one is like, yeah. If they this is what important. I mean, this is what happens in research. You need to be published fast before other people publish it. Okay. So if that happens, then the worst thing is like, yeah, you can't do much about it. You have to cite their work, unless and then if you're using the same methods, but yet your data use is different, and yet you prove something is wrong against what they claim, then you can publish it. Right? But if you do this, if you conduct your research now, someone is also doing it, and yet both of you happens to produce the same results, the same using different data, but the same results, then there's nothing much you can do because he published before you. But if you happens to show that the result is different, then you can actually cite his work and prove his work is wrong. But you have to be careful with that when you do that. Make sure that you actually do your research properly, because indirectly you actually have cost. By doing that, you actually already found contributions. Okay. The only thing you can publish is when your results show otherwise of their results. If you give the same output, even your idea is different, or I mean they're almost the same as your idea, and there's no significant idea, then there's nothing much you can do. Just have to find more things. Try to find something out of, not out of something. Just try to find something different out of it.
and better, I think.
Maybe try
With
to adjust your
judgment.
parameters, because there's a lot of things you can do. Even though someone is doing the same thing, you can always like modify the parameters, this and that, and test the
Yeah.
experiments until you get better than theirs or worse than theirs.
Yeah. Thank you very much for the insight. Yeah. The contribution is the most important thing, and to make our contribution is different enough and better. Yeah. Good idea for adjusting parameters. Thank you, Dr. Liu.
Yeah, you just that's where you need that's where you need my statistical test to make sure that you show that it's different. But whether it's better or worse doesn't matter, because they already show something. They will definitely say they are good, but if you show them they are bad, you can actually claim they are bad. If you test they are bad. Yeah.
Okay, thank you very much. The next question is actually from me. I wanna ask a question regarding your presentation. Is that okay?
Yeah, fine.
Yeah. Okay. As you explained, that evaluation, especially comparison with other research, is very important. We usually want to prove that our proposed method is better than the previous research. However, yeah, as you mentioned, that it is difficult to obtain the same data set that were used in the previous research. Yeah. So I want to know, what is your suggestion regarding this problem? Can we collect data set with similar characteristic with the previous research and then compare the result directly, or we should replicate their code, their method, and run it in our data set? Thank you.
Okay, there's two ways you can do that. The first and easiest way is contact the researcher.
Wow.
Okay, that's the first way. Contact the researcher, ask them, can I have your, even you can ask them, can I have your, I'm interested in your work, can I have your algorithm, can I have your data, I'd like to test it out and compare with my algorithms. I bet they'll be happy to do that, because usually when you do that, you have to cite their work. Okay. Second thing you're talking about, can you replicate as much as information that you can based on the paper, based on the information provided on their publications? I would say yes, you can try to do that, but make sure you highlight what you follows, okay, and what you can't follows, and the assumption that you made. Okay. Am I saying that the algorithm is different, or you're trying to run your experiments with your data and their data? It's a question.
Yeah. Thank you very much for the answer, Dr. Liu. Yeah.
Yeah.
It's very clear. Yeah. Yeah. We should contact the researcher first to
Yeah,
ask
that's the first thing to do.
whether
Contact the
we
researcher first. Yes.
yeah whether we can use their data and method.
And whether they can,
Okay,
and ask
the
them to
last
share the
question.
data.
Okay. Yeah, okay. Thank you very much.
Yes.
Okay, maybe this is the last question if there is no okay. The last question is from Mr. Putra Firdaus from ITS. Yeah. What if we want to do a research that have no preliminary research? So we cannot find previous research that's similar with our research, so that we cannot compare it with previous research. How we express it in our experiment.
So if you can't find previous work, then
Yeah.
most probably you can, I mean, I assume that it's something new. So what you can do is you can compare. You can't compare with another algorithms, but you can compare your algorithms with different data sets. Change your data environments, change your data sets, and also try to change your parameters. Okay. So I mean,
Okay.
yeah.
Okay. Thank you very much. Yeah. I think we can always find similarities with previous research, whether it is from the data or methodology or maybe application. Yeah.
Yeah.
Thank you very much.
Definitely there's a way you can find it. I mean, whatever area that you work on, definitely there's some similarity that you can test it out. I mean, unless you're really working on something that is like so limited, then yeah.
Okay. Actually, there is another question from Mrs. Anindya from ITS. She want to ask, which one is better? Is it to make our model specific to a certain system, or rather to make our model more general so that it can be applied to many systems? Which one is
Usually,
better?
usually you try to, I will not say more general or more specific, but it should be uh, specific to the problem domain that you're trying to solve. Okay, but as realistic as possible. Okay, when you generalize your environment, then you might be tense yourself to result in multiple parameters that will affect your outcome. But the problem is like you won't know which one is your main issue here. So usually when you're trying to do your experiments, you're trying to, because usually you have your problem statements, then you'll be able to know that, okay, this is a problem statement, this is the environment you're interested in. So you try to be more specific to the problem domain you're trying to solve, or the area that you're trying to apply your system to.
Okay, thank you very much for the answer, Dr. Lim. I hope it answered your question, Mrs. Anindya. Yeah, because if the model is too general, it will be difficult to optimize the parameter.
Yeah.
Yeah, for your model.
And also general, how do you define
Okay,
general?
I think. Yeah, general is too broad.
Yeah, you can't define
Okay.
general.
Okay, thank you very much, Dr. Lim. Yeah, yeah. I think that's all of the questions. Sorry. There is another question from Mr. or Mrs. Lee Xiangyu from University Technology Malaysia. If the data is not a normal distribution, we transfer it useful. Is it a useful way to test and analyze to change the distribution of the data? Is it a good practice for analyzing the data, changing the distribution?
You can't, okay, to answer your first question, to answer your question, your data distribution, you can't change because that is actually your data, right? It's the data that you collected from experiments. So no point you change your data distributions. So if your data is not normal, then don't use normal distribution tests. Use a non-parametric test like the median and the quartiles. And also there's also non-parametric statistical tests like Mann-Whitley and Delany. You don't have to stick to your t-test or your means. As I say, the best approach is just to use non-parametrics. Use your median and use your KS test or your Mann-Whitley test. And to change your, there's no, and it's not a good practice to change the distribution of the data because you never know that the non-distributed the non-normalized data maybe show something better, right? Because to us data is important. Why you want to change your data from non-normal to normal, right? And to answer the question again, sometimes you can also run the experiments. I mean, collect more data. Okay, you try to collect more data. You might eventually make your data become normalized as well. I mean, you can get your normal distributions. Okay, but I don't know how much more you need. But if you get enough sample data, you might ever end up with normal distributions. But when you get that, will that actually affect? Does it actually shows the real output of your algorithms? I don't know, right? Because usually you want to find a time, because I have another approach that actually, I mean, I have another ways that you can actually stop. Yeah, I mean, there's also an approach that you can actually try to decide when you have enough data sets. Because sometimes, as I say, try to collect as much data as possible. You don't do experiment with only 10 data or 5 data. You need at least like 25, 35, 50, 100. But which one is how do I know how much data I need? And I can't run my experiment forever because it's expensive to run experiments. So I need to find a way to stop as well. So, yeah. But to convert your data from normal to non-normal, there's no, I mean, if you have already data sets, there's no way you can do that, but only try to add more data.
Okay, thank you very much for the answer, Dr. Lim. I think it's quite clear. Yeah. Okay. Yeah, this is such an interesting and insightful discussion. But unfortunately, the time is running out, and we must conclude our discussion today. Yeah. From the presentation from Dr. Lim, I conclude that our research should be based on evidence, and our findings should be reliable and credible. Our results should be at specific level of confidence. It should be consistent, unbiased, and repeatable over time. And to achieve that, we should methodologically develop our research. By first, we need to formulate the research question in which we make our research hypothesis. And then second, we collect the data. What data will be used? And then we need to understand the data characteristic. And then the third, we need to evaluate our result. In this, we can use hypothesis testing approach to evaluate whether our hypothesis should be rejected or not, or to compare whether our result is better than the result of other research. The more experiments that we run, the more data that we collect, the better the result that we get. And then the last, we need to present the result so that it will be understandable by the reader. Okay, thank you very much once again to our honored speaker. Thank you very much, Dr. Lim, for sharing your experience and expertise regarding this topic. And now I will pass the session to our Master of Ceremony, Ms. Bonara. Thank you.
Okay, thank you very much, Dr. Lim, for the excellent lecture today. And thank you, Dr. Rarasmaya, for conducting this amazing session. Okay, please give applause to Dr. Lim and Dr. Rarasmaya by using the Zoom reaction feature for today's amazing session. Furthermore, we would like to present a certificate awarding for our honorable speaker and moderator. Okay, please, the committee. Okay, this is the certificate presented for Dr. Lim and Dr. Rarasmaya.
Thank you very much.
Okay. Okay, once again, thank you very much to our speaker and moderator for your availability on today's session. Okay, before we end today's session, we invite you all participants as well as the honorable speaker and moderator to take a group photo. So for the participants, please open your camera. Okay, I will wait until the participants open their camera. Okay. Now I will start counting down, so please give us your best and sweetest smile. Okay, 1, 2, 3. Once again, 1, 2, 3. Okay, now we've finished the group photo. Then for the participants, please fill the feedback form through the link bit.ly/feedback R2SEP 2021 that you can also see on the Zoom chat room. We want to remind you that participant who will get a stamp for it is the participant who come on time, join this event until the end, and also fill the feedback form. Finally, we have reached the end of today's Researcher and Research Student Enrichment Program, and we sincerely apologize for any mistakes we may have made in presenting as Masters of Ceremony and Committee. Thank you very much to Dr. Lim and Dr. Rarasmaya and all participants for the attention and cooperation. Before we part, I would like to inform you that we still have several future agendas in R2SEP. You can see it on the poster we are showing you right now, or you can check it out in ITS Global Engagement website later. We will see you in the next session in the next 2 weeks with the STEM research management skill that will be delivered by Dr. Muhammad Ali Tarek from Malaysia Japan International Institute of Technology, UTM, that will be conducted on 30 12:30 p.m. on Thursday, on the 23rd and 27th of May 2021. Once again, thank you very much, everyone, and good evening. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam
Waalaikumsalam.
warahmatullahi wabarakatuh.
Gimana Dr. Lala?
Alright, thank you again to Dr. Lim and Dr. Rarasmaya, and also Dr. Irfan who joined us today. Dr. Irfan is our Senior Manager for International Partnership at ITS Global Engagement. And also thank you to all committee and participants who joined the meeting today. Please allow me to end the session in 3, 2, 1. Thank you.